A complete fault of a quadrotor's propeller is considered. Such fault has been already detected. The motor, aligned on the same quadrotor axis of the broken one, has been turned off too. The resulting configuration is a birotor with fixed propellers. A backstepping approach for translational movements is employed together with a PID-based control for angular displacements. Then, any point in the 3D Cartesian space can be reached by the birotor. The price to pay is the impossibility to control the yaw angle since the birotor continuously rotates around its vertical axis. A diagonal emergency landing trajectory has been considered. The initial and final linear velocities and accelerations are put to zero. At the end, the birotor stays for other 10 seconds in a steady-state condition. It is possible to notice that the errors are restrained and the tracking is accurate. The visible oscillations are due to the continuous spinning of the birotor around its vertical axis. The uncontrolled roll angle is shown. The commanded propeller velocities do not saturate. The same emergency landing trajectory of before has been considered, but white noise has been added to measurement signals. Moreover, roll and pitch angles do not start from a zero condition. The errors remain bounded as well as the uncontrolled variables, while the commanded propeller speeds do not saturate. The presence of an obstacle is now considered. Hence, first a semicircle has been planned to avoid such an obstacle, then a vertical straight line towards the origin of the Cartesian space is performed. The duration of the first part is 20 seconds, while the vertical straight line path has a duration of 25 seconds. The vehicle stays in steady state for 5 seconds. The tracking is again accurate. The uncontrolled variables remain bounded. The commanded propeller speeds do not saturate. A spiral path is now taken into account. The duration of the trajectory is 55 seconds. This shows that, in principle, any emergency landing trajectory can be considered. To summarize, giving the desired references for the position, the altitude error is computed and then the quote is regulated through a PID-based controller. The planar X and Y components are controlled thanks to a standard backstopping approach, whose stability has been provided through a Lyapunov-based method. The desired reference for the pitch angle is retrieved by the previous control actions and it is controlled through a PID-based controller. Even for the spiral case, the tracking is accurate. The uncontrolled variables remain bounded and the commanded propeller speed do not saturate. The values of the error is affected by both the birotor spinning and the highly varying planned path.